We are now discussing the higher dimensional version of Taylor's theorem, and this is also called Taylor's theorem, and this is also called Lagrange form, the one I'm discussing now as in the single variable case. So we're back to the same setting. We have some function on an open subset of Rn, which is called f. The subset is U. And this function is supposed to be k plus 1 times differentiable for some number k plus 1 there for technical reasons. Now, the statement is now similar. We need some point at which we want to approximate f by the Taylor polynomials. So we take a point a in U, and usually if we are in a single variable case, we had something on an interval, and we would just find there was in the Lagrange form there was some time in the interval in between. Here it's a bit delicate. We need to introduce one more condition, namely we take a in U and we take h in Rn. Not only such that a plus h is in U, so it's a slight, it's close to a. It's the idea here. So a plus h is in U, but we need a bit more. We need that a plus t, plus t times h is in U for all t in 0, 1. So again, as we had in an earlier situation, this is the line segment from a to a plus h. So not only a plus h is in there, but the whole segment there is contained in U. Okay, this is what we need. And then we can apply the Lagrange form of Taylor's theorem, namely then there exists some parameter theta between 0 and 1 such that, sorry, just made a little mistake in the statement. So the idea is now that f of a plus h is now given by the Taylor polynomial t k f in the variable h at the point a plus, and now in the Lagrange form in the single variable version we basically had something which looked like the additional summand of the Taylor polynomial just at some time theta in the interval, some different time in the interval, and here it's almost the same. Here we get d to the k plus 1, so the derivative 1 higher, which is why we need this assumption here, f, and then also taken in h with the inputs h, and in the same way this always corresponds to the Taylor polynomial divided by k plus 1 factorial. But here I've skipped the point, so the point is now given. So before we had some time in the interval, and here it's just some point between, roughly said, between a and a plus h, and this is expressed by taking a plus theta times h. So there is some point on the line segment between a and a plus h, such that we can take this expression here, which almost looks like the additional summand you get if you take the k plus first Taylor polynomial instead of the kth one. Okay, this is the statement of Taylor's theorem. So this tells us it's almost this, the idea is kind of it deviates from this polynomial by this expression here. Now, how to see this? The idea is now really to just trace it back to the one-dimensional setting and to use the single variable Taylor theorem, the Lagrange form, and then re-obtain the multi-dimensional one. Now, the idea is simple of how to trace it back, namely we take g from 0, 1 to u, sorry, not to u, to r. Namely, g of t is just supposed to be f of a plus th. This is well defined because we've made this assumption here. So we just want to study this one and then apply Taylor's formula to this. So, or Taylor's theorem for the single variable case. To relate this to the derivatives of f, we can just write this again, g as the composition of f composed with gamma, where gamma from 0, 1 to u is just the map gamma of t is a plus t h. So that's parameterizing the line segment, it's a curve in Rn. Okay, now this is what we have seen so far, and since gamma is obviously k plus 1 times differentiable, I mean, if you just derive this curve here, what you get gamma prime is just constant h. If you derive it again, you get 0, and this you can derive again and again and again, and you get 0. So you can derive this as often as you want. So this is a composition of, so G is a composition of two k times 1 differential, k plus 1 times differentiable maps. So G is k plus 1 times differentiable. This is something I haven't proven explicitly, but compositions of n times differentiable maps are again n times differentiable. This is what you can see from the partial derivatives, and this is easy to follow, so I haven't proven this in the lecture. Now, this means we have enough differentiability here, and so now by the one-dimensional Taylor, so Taylor's theorem in Lagrange form, this was theorem 436 in Mathematics 1. We can now just apply this formula to this map G, which just single variable and R valued. So we know that for each, so we get colon for each x in 0, 1, there exists some theta between 0 and x. So we take as we evaluate, or we take the Taylor series in the point 0. The Taylor polynomials in the point 0. So for each x there exists some theta between 0 and x such that g of x is, and now we have the Taylor polynomial, which I write down explicitly here in the single variable case, the sum from r equals 0 to k, and now we have g to the kth derivative in 0 divided by k factorial times x to the k, plus, and this was the additional term in the Lagrange form, g k plus 1, so the k plus first derivative in theta divided by k plus 1 factorial times x to the k plus 1. This was the Lagrange form of Taylor's theorem. So in particular, if we let x be equal to 1, we get that g of 1, then of course all the powers are just 1, 2 that appear there. This is the sum from r equals 0 to k of g to the r of 0 divided by k factorial plus the k plus first derivative of g in theta divided by k plus 1 factorial. And the rest is just as it is. And now we can just insert the definition of g, namely g is f composed with gamma. So g of 1 is f of gamma of 1, which is nothing but f of a plus h. And here we just expand the first summand, which is just g of 0, which is nothing but f of h by definition of g, plus, and then the remaining terms are from 1 to k, rth derivative of g in 0 divided by r this is of course r factorial, not k factorial. I'm afraid I made the same mistake here. Sorry about that. Anyway, so this is this sum plus the remaining summand. And now it's clear what we have to do. We need to compute the higher derivatives of g, because we just have to bring this together, like this. We just have to bring this together with the derivatives of f, and to see that these terms here, that basically this here is precisely the kth Taylor polynomial of f, if we write this down in explicit terms. And this is the remaining part that was part of the claim. So that, here we got it, this is this, and this corresponds to that. Okay, for this we need to compute the derivatives of g, and I make this a separate claim inside the proof, which I will prove individually. So the idea is g, the rth derivative of g in t is the same as dr in the point gamma of t, where gamma is defined as above. of h, and so on to h for all t in 0, 1, and for all r between 1 and k plus 1. Okay, how to see this? This is again shown by induction over R. So by induction over R. And so the base case, so R equal to 1. This is what we've already seen, because this is a particular form of this one corollary, where we saw that if a function is given as so a single variable function is given as the composition of a curve and some function from Rn to R, then we have this simple formula for the derivatives, namely this was corollary 1229. G prime of t is the same as f composed with gamma prime of t. So this is by that corollary nothing but df in the point gamma of t of gamma prime of t. But since gamma is just, said it before, simply this expression here, the derivative is just h, the constant vector h. So this shows that g prime of t is df in the point gamma of t of h, which is the base case. This is r equals 1. Okay. Now for the induction step. Okay, for this we assume that, assume as induction hypothesis that we've shown the claim. Let's just call this equation star. So this is star. Assume and here's the simple hypothesis that star holds for some value of r between 1 and k. And now we want to show this for r plus 1 in this setting. So then, first of all, so we know that g prime of r has this form, and for this form we can now, here's an f missing, sorry about that. Like that, sorry about, I hope this wasn't confusing. So for this abstract higher differential, we have seen that we have these explicit formulas to compute them. And this is what we will use now. We will write this in this explicit formula by partial derivatives and then derive again. And basically then sort all the terms and see that the right thing comes out in the end. Okay, assume that this holds. So by theorem definition 1248, then we compute that g r of t, so the rth derivative of g and t. This is now this expression here, and by that theorem we have that this is the sum from I1 equals 1 to n to IR equals 1 to n, partial I1 to IRF in the point A, times, and now it's just the corresponding, since we've just included h, as we've seen before. This is just the components of h here now included, so hi1, hi2 to HIR, where, so this denotes the components, so h, which we consider as some fixed element, it has just components h1 to hn, as we always consider. Okay, this is a formula that we're having here, and we've seen, or we know by assumption, that f is k plus 1 times continuously differentiable. Continuously differentiable. Oops. Sorry about that, I haven't formally introduced k plus 1 times differentiability here, just the continuous version. So, but by this property, this means that these partial derivatives, since r is at most k, these are all differentiable. And this means we can just derive this expression here again. and, sorry, another mistake. This is not in A, but in gamma of t, since we're in there, yeah, right, we have this point gamma of t in here, sorry about that, in gamma of t. Now, these are differentiable again, and we know that gamma is differentiable itself, so these are again differentiable. So, by assumption, d, the partial derivatives di1 to er f composed with gamma is differentiable for all I1 to IR between 1 and n. And so we need to derive this expression here by t to get the right formula, and this is what I will do after erasing. If we take the previous expression and derive it by t, this becomes g up this first derivative in t is, and now of course derivatives are compatible with sums and with scalars, so this is the sum from I1 to n to IR equals 1 to n, so this sequence of sums here, and then we get di1 to IR composed with of f composed with gamma prime of t times hi1 to HIR. And now again, this is a composition of a curve and a map a function from a subset of Rn to R. So we can again use the very same formula as before. So this is the same as this big sum of d of di1 to IRF in the point gamma of t applied to gamma prime of t, hi1 to HIR, and as we've seen before, this gamma prime is just h, and now this can be then computed in partial derivatives, and there we use this expression of the differential in partial derivatives, meaning we get here the sum from I1 is 1 to n to IR is 1 to n of and we get another sum in there, namely IR plus 1 equals 1 to n, and now this is the same as DIR plus 1, I1 to IR. So this guy here derived in the IR plus 1 direction of f in the point gamma of t times the IR plus 1 component of h, which is HIR plus 1, and we still have hi1 to HIR. Now, the only thing that's disturbing here, or that's not working, is the order of derivation here. But it turns out this is irrelevant, because by Schwarz's theorem, we know that the order of partial derivatives doesn't matter. So if we change the order of two of them, this gives the same derivative. So derivation first by I and j is the same as first j then I. So if we just apply this to this expression here, we get that r plus 1, comma I1 to IR, which is just the sequence of partial derivatives, would be the same if we just swap these two. So this is the same as di1 IR plus 1, then the next would be I2 to IR of f, and now we could swap again, so this would be the same as di1 I2 IR plus 1 and so on to IR of f, and then we could swap again and again and again and again, and eventually we would achieve, so this was, if we just do this so long until this one has arrived at the end, so this is the same as di1 to IR plus 1f. So applying this here and just swapping the order here, and here this is of course the order of multiplication is irrelevant, so it follows the r plus first derivative in t of g in t is the sum from I1 equals 1 to n to the sum of I r plus 1 equals 1 to n di1 to I r plus 1 f in gamma of t times hi1 to times hi r plus 1. And if we now take a look at this formula, again, now we're doing this in reverse. This is the same as, so this was again theorem definition 1248. This is the same as dr plus 1 of f in the point gamma of t and with variables h to h. And this is what we wanted to see. So if we insert now, so this proves the claim. So this finishes that part of the proof. And now, in particular, this means, in particular, so I don't have the original Taylor formula I had before. So if t is equal to 0, which appeared in that formula, then we just get gamma of 0, which is a. And now we had this point theta there that appeared in the Taylor theorem of applied to G. In particular, this means that G r plus, k plus 1, k plus first derivative in theta, which appeared in that expression, this is the same as dk plus 1 f in the point gamma of theta, and by definition this is just a plus theta times h, evaluated in h, and so on. And this is what we wanted to show. So if we just insert this in the above formula, this shows the claim. Okay, this is the Lagrange form of Taylor's theorem. As in the single variable case, there's also a Péano form of Taylor's theorem, which I want to state next, and I will not prove that form. It's a bit tedious and a bit technical, so I've included a full proof in the lecture notes, so you can really read this up there nicely. But to get the idea, the statement should be enough at first sight. So if we take the Taylor's theorem in Péano form. So this looks the following way. We have almost the same assumptions as before, so that k and n in n, u in Rn open, f from u to r is, this time it suffices to take k times differentiable, and we take a point A in U. And we want, f is k times differentiable, A in U. And now we take the following set, U prime should be defined as the set of all H in Rn. And this time we do not want only those H for which A plus H is in U, but such that A plus TH is in U for all t between 0 and 1, so we can apply basically the Lagrange form of Taylor's theorem. Okay, if we have all these things given, so f, and this is kind of a, intuitively this is some neighborhood of the point A, then there exists a map phi k from U prime to R, such that, first of all, f of A plus H is the kth Taylor polynomial of f in the variable H in the point A plus phi k of H. And now phi k is kind of measuring the difference between f and the Taylor polynomial. And the idea is now here that the limit as H goes to 0 of phi k of H divided by the norm of H to the power of k, so Euclidean norm, this is 0. Okay, meaning this is some complicated function, this is a polynomial of degree k, and the polynomial has this property that the difference between f and tk, which we would get by subtracting this on both sides, this difference here is so small that it grows smaller than some polynomial of degree k. So this is the idea here, that this is again, this has the approximation property that we expected, that this is the best approximation of f by some polynomial here. And this is what I will state this as a remark in a second, so let me just note, so here the proof is in the lecture notes. And this is just some, it's quite instructive, I would say, because it contains a lot of standard analysis calculations. So it's maybe, if you're interested in these things, you can see and want to work with epsilons and deltas and play around, then you can just study the proof, because it's actually a really nice proof, but not that relevant at the moment. So the idea is now, and let me formalize this, what I just said, as a remark, 1255. So the interpretation of this theorem of the Péano form, so of theorem 1254, TKFA, TKF, yeah, in the variable here I leave open in the point A, is the best approximation of f by best approximation of f by a polynomial of degree smaller than or equal to k near a. And this is the important thing that should also be, again, imprinted in your brain. This is the idea of Taylor. And this is something where you think, okay, by hand this is really annoying, but the good thing is to compute these polynomials, there's procedures, there's algorithms. This is something you can feed in a computer. If you have a complicated function f, it's no problem for a computer to compute a polynomial of degree 1000, for example. Then you have still the function, which is not handy for us, of course, to do things by hand, but for a computer, while in fact f might be involve some complicated operations. So the computer might be much faster to compute some things for this polynomial of degree 1000 than for the original function. And of course, if you can then see that the difference between those two is very small, and if you know that you only want to study the function in a certain neighborhood of a point, then this gives you, this helps you really in approximating things in the computing stuff. And this is how you really approximate complicated things and how you tell computers to do complicated things. Give them an algorithm of how to compute this polynomial and then compute stuff for polynomials, and they're good at it. Okay, so I haven't proven that one, but this aspect of best approximation of a polynomial. The question is, of course, when is it a good approximation, or what could we expect? And for this, and also for illustrating what I did before, because this was quite abstract, I must admit, I will now compute something for a concrete example. So I will write down an explicit function and really compute Taylor polynomials, namely, but only the second one so far, because otherwise it's just not very insightful, but just taking a long time to compute by hand. Namely, we study the function f from R3 to R, f of x, y, z is given by the sine of x squared times y plus z. Okay, this involves the sine, which is a little complicated function, so a bit more complicated than polynomials. At least for computational purposes, polynomials are always much nicer. And the question is now, how can we approximate this by polynomials? And the point at which we want to approximate this shall be a to be the point 1, 0, 0, which is a point in R3. Of course, there's one geometric problem here. This is a function from R3 to R, so its graph is a subset of R4, and this I obviously can't draw. So there will be no drawing for this, but I hope it's still understandable. So we want to compute the second Taylor polynomial of f in a variable in this point A. So in this point that was given there. So for this purpose, we compute partial derivatives. I'm not mentioning here, so I have the full explicit details in the lecture notes. So I will leave away and not write every single thing down, but you get the idea there. So if you want the full details, look in the lecture notes. So this is obviously, to see that this is continuously partially differentiable as often as you want. So k times for every k. In particular, this is twice continuously differentiable, which is easy to see. Now, compute the partial derivatives first. which we obviously need to compute the Taylor polynomial. So, the first order partial derivatives d1 f of x, y, z. So derive this expression by x, which by the chain rule is, first of all, the cosine of this what's inside, and then here derive this by x, and the derivative of x squared y by x, this is 2xy. So we get 2xy times the cosine of x squared y plus z, d2f x, y, z. So deriving this by y, this time x squared is treated as a constant, so this is the derivative on the inside, x squared times the cosine of x squared y plus z. And finally the derivative in the z component. So if we derive this by z, the interior derivative is just 1, so all we get is the cosine of x squared y plus 2. Okay, now we need to compute all the second order derivatives, and I need more space for that, so let me erase and then discuss this example. Okay, from these expressions here, we want to compute the second order partial derivatives. And yeah, for this, we basically need to derive these expressions again, which is not that exciting. Let me just do the first example. Okay, let's derive this by x. So this can be done by the product rule. Yeah, you need the product rule for this. Let me abbreviate. This is just, so if we derive first, yeah, so this is 2x times this expression here, so derivative of 2x is 2. So the first one is 2y cosine of x squared y plus z, and then the next one is derived by the chain rule again, and you eventually get 4x squared y squared. The interior derivative is again 2xy. And now for this becomes a minus because the derivative of the cosine is minus sinus. And this gets that. Okay, this is the first of the partial derivatives. It's a bit tedious, isn't it? Wait a second. Yes, hello, support. Yeah, could you insert the partial derivatives at this point? Oh, thanks guys, you're the best. Okay, that saved us some time. So, now we've got the partial derivatives, and now we want to, yeah, we have to evaluate them in this point 1, 0, 0, of course, but we first want to compute the Taylor polynomial. So, we have computed the Taylor polynomial using the formulas for this. I mean, I had this explicit expression in terms of partial derivatives. We just have to write this down now in that special case that we're in. So, T2f, and now let's call the argument again v, in the point 1, 0, 0. So, yeah, or v is now given by v1, v2, v3. I'm not repeating this again. So, this is by definition. So, yeah, the way we computed this, first f of 1, 0, 0. Then we get, yeah, 1 over 1 factorial, but we get the sum from 1 to 3 of the first order derivative dif in 1, 0, 0 times vi plus, and now I'm already, not economic with the space here. And then the second order partial derivatives, there let me call the indices I and j for simplicity. So we take this double sum, there's not, so we have 1 over 2 factorial here as a constant factor, so this is 1 over 2. So we have the sum from I equals 1 to 3, from j equals 1 to 3, dij f1, 0, 0, vi, vj. Okay, this is now, of course, something we can write down without the summation signs easily because there's not that many summands. So we just need to just write them down explicitly. So let's do that. So f of 1, 0, 0 plus d1f in 1, 0, 0 v1 plus d2f in 1, 0, 0 v2 plus d3f in 1, 0, 0 v3, and the remaining terms here. This is 1 over 2, and now we get d1, 1 f of 1, 0, 0 times v1 squared. Okay, plus D1, 2, F in 1, 0, 0. And here we can bundle because we have, first of all, V1, V2, but this is the same as D2, 1. So we once get this term with V1, V2, and yeah, then with V2, V1, which is just twice this guy. So we can just take this, whoops, twice. Okay. The same thing with 1 and 3, so we get twice D1, 3, F in 1, 0, 0, V1, V3. Okay. Now what's still missing? We have D2, 2. This is only there once. V1, 0, 0 times V2 squared. Plus, and now we again have twice D2, 3. Again, it pops up 2 individual times. So D2, 3, F1, 0, 0, V2, V3. And finally, D3, 3, F in 1, 0, 0 times V3 squared. And now close the big bracket. Okay, now this is what we have to explicitly compute, and the good news is that a lot of this is vanishing, so this becomes quite not as difficult as you might think it is. But this, I mean, this is not difficult. This is just a lot of things to write down and to compute. But this is just once you got the scheme, this is always the same. Okay, f of 1, 0, 0. What do we got? F was okay. Now f is not on the blackboard anymore. Let me scribble this here in the corner. F of x, y, z is the sine of x squared y plus z. So if we're in 1, 0, 0, we have 1 times 0 plus 0, so the sine of 0, which is 0. Okay, what is the partial derivative d1 in 1, 0, 0? Here we have, okay, this is 2 times 1 times 0 times something, but the 0 is already telling us it's not, it's just 0. So for d2, let's check here. Here it gets more interesting. Here we have the cosine of 0, which is 1, and we have x equal to 1. So it's indeed 1. Okay, for the third, this argument here you have the cosine of 0, which is also just 1. Okay, now we come to the second order derivative. So 1 over 2 times, okay, d11 f0, d11 is here. Okay, here we have sine of 0 included, or here's a 0, so, okay, here's a 0, here's a 0, so this will vanish. So 0 times v1 squared plus, so now 2 times d12, so d12 is here. So this is 1 times the cosine of 0, which is 2 times 1 times 1, which is 2. This here vanishes, so this is times 2 times v, sorry, now I'm getting mixed up, so v1, v2, and so on and so on. So let me maybe abbreviate this. Yeah, I think this was already everything, yeah, plus, and a lot of zeros. So yeah, I'm not doing full computation here, but the other derivatives, you can easily check that they vanish in that point. So if we summarize everything, all that remains is v2 plus v3 plus, and here we have 4 times 1 over 2, which gives 2 v1 v2. And this is the Taylor polynomial. This is a polynomial in the entries of v. This is a polynomial of degree 2. This is here a power of degree 2, a product of 2 entries of the vector. So this is our Taylor polynomial. This is the polynomial that approximates this function f best in the, near the point 1, 0, 0. But the question is, so how good is this approximation? And now we can do the computation there. We know a bit by the Péano theorem, so this is some qualitative statement about what the remainder does. But one computes, and this is what I've done in the lecture notes, and it's probably not even the best estimate, so it might be even a much better statement there. Sorry, I just made a little mistake. So when you ask how good this approximation is, you of course need to ask how close you need to be to the point. And so the question is kind of, when I'm this and this close to the point itself, how good is my approximation? And what I'm doing in the lecture notes is to show that for V, if V is in a neighborhood, in an open ball of radius 1/10, around 1, 0, 0. So a reasonably small ball around this point 1, 0, 0, where the distance is smaller than 1/10. Then I can show that the difference of f, which would be then f of 1, 0, 0 plus v, this is what's approximated by the polynomial, minus t2f of v in 1, 0, 0. So this is really here the difference between those two terms, that as long as v is in this ball around the point, then this is smaller than or equal to 1/1000 plus 1/3072, which is roughly 0.0013. So you see the difference if we're in this small neighborhood, and if we're just interested in studying this locally, the function there in this small neighborhood for some reason, because, I don't know, this model is a physical situation where we're only interested in this particular part, then the difference here is so this is kind of the error that you get if you replace the function by the Taylor polynomial. And then, of course, it's up to you to decide if this is good, but as you see, this is a very small number, maybe surprisingly small. So this shows that really this is a quite good approximation, but this gives you then how bad your estimate can be, or what could be the error in your measurement if you replace, or in your computation if you replace the function by the approximating polynomial. Okay, the details of this are in the lecture notes. Just some standard calculus stuff, nothing wild, but it's a combination of several estimates. So this is all I wanted to say about Taylor. There is a lot more to do this. There are a lot more, more computational explicit formulas where you can kind of summarize some things, but this is not that important for you now at this point. So instead, we want to focus on the next chapter on the second derivative. Namely, the idea is that for single variable functions, we have seen that local extrema are defined in terms of the higher derivatives. So if the second derivative of a single variable function is positive or negative, this in a point where the first derivative is vanishing, this tells us if we have a local maximum or local minimum there. And there's a similar classification of this for higher dimensional functions. And this is what we will discuss in the next section. And we will discuss a bit of linear algebra that we will need for this point, which I have skipped so far and which I want to introduce now in the upcoming section. See you in the next section.